We were talking about interior point method or barrier method for linear programming. So let me remind you, I know it was about a week back when we last discussed it. So I want to minimize C transpose X such that AX is equal to B, X is greater than equal to 0. This was my problem statement. And if you recall, in the argument in the manifold suboptimization method was, we are trying to optimize a function over this box, and then I have to go along the edges of the box in order to get to the optimal solution. And what the barrier method is trying to tell us is, if I have to go from this corner to that corner, of course I can go along the edges and I can reach that corner, but it would be more efficient if I could just go through the set to that particular corner. So that's what this barrier method is trying to do. So we are going to be in the interior of the set, and we will reach the optimal solution through the interior of the set. And in order to do that, we define this function f epsilon of x, which is C transpose x minus epsilon summation log of xi. I goes from 1 to n. And I have my set S as Z in Rn, or maybe X in Rn. Ax equals to B, X is greater than equal to 0. So as xi is approaching 0, this term is approaching negative infinity. I'm multiplying it by a negative epsilon sign, so this whole term is going to go to positive infinity. So in some sense, f epsilon x will have a solution. If I want to minimize this function, I'll have a solution within this particular set. So my x star epsilon was defined as argmin x in S, f epsilon of x. And this is the central path traces, or for epsilon going from epsilon infinity to 0, this gives me central path. And the algorithm is trace the central path. So this is what we discussed in the previous lecture. This is an overview of where we stopped last Monday. Yes.
For S, like you said, x is greater than or equal to 0.
Yeah, this one is always greater than 0 because at 0, this particular term is undefined. It's minus infinity. So f epsilon x will go to plus infinity. Okay. So we want to trace the central path. So we want to start with some epsilon greater than 0, some large number, 100, 200, 500, whatever. And I want to get to the central path, which is x star of 100. And then once I reach x star of 100, I want to go to x star of 99, x star of 97, 90, 80, 10, 0.1, 0.001, and so on and so forth. And x star of 0, which means that I'm minimizing this function over this set, I'll reach the optimal solution. But of course, I'm not going to go to x star of 0. I'll stop at x star of 0.00001, and that would be my approximately optimal solution, and I'll be happy ever after. So the algorithm that we are talking about is from 1984. The researcher was in IBM IBM Research / AT&T Bell Labs at that point of time. So the researchers was in during the transition phase. So it's kind of difficult to figure out whether the work was done at IBM or whether the work was done at AT&T Bell Labs. But anyways, AT&T Bell Labs had filed for a patent for this particular algorithm, and they created a chip in order that implemented this algorithm that we'll be talking about today, and sold that chip to Pentagon for whatever reason. Okay. As I said, the first application of optimization is movement of troops during the war. So the algorithm that we are talking about was used in Gulf War in 1990s. Okay. So what's the idea? So I want to trace the central path. So I want to get close to x star of 100, and then I want to trace the central path, and I want to get to x star of 0.00001. So how do I do that? So there are three questions. How do I know that I'm close to central path? And then question 2 and 3 are how to pick epsilon k and how many Newton's iterations to do. How many, let me say, gradient steps I need to take. Okay, so I'm standing. So I start with some random initial condition. I reach the central path. How do I know that I've reached the central path? How do I know I'm far away from the central path? So that's question number 1. And question number 2 and 3 are sort of interrelated. Once I've reached the central path, I need to reduce the value of epsilon, and then I need to figure out. So now x star of epsilon k minus 1, I'm standing there, or I'm probably standing at xk minus 1, and I need to figure out how many Newton step or how many gradient steps I need to take in order to reach the central path all over again, and then reduce epsilon k and so on and so forth. Okay, so that's what we are going to be talking about today. Let's try to, I mean, this is a very complicated set of problems. So let's try to think from first principles. Let's say I'm standing at x and I want to take 1 Newton step. Okay, so we know that Newton's step is the best method. Newton's method is the best method. I can compute what the direction for my gradient descent should be if I'm using Newton's method. So let's try to solve that. So I'm standing at x. Compute x bar. So what is x bar? X bar equals to argmin z in Rn gradient f epsilon x transpose z minus x plus half z minus x transpose such that Az equals to B. How many of you think this is an easy problem to solve? Is it easy or difficult? So I have to compute the gradient. Okay, so let's try to figure out what the gradient and second derivative is. But then I have this constraint Az equals to B. How do we solve problems of this type? Az equals to B. This would be a convex problem. So hopefully this is going to be a positive definite matrix. We'll see. We'll make sure that this one is a positive definite matrix. So it's a convex problem over a set of equality constraint. we can use Lagrange multiplier theorem to solve this particular problem, and we get the optimal solution because it's a convex problem. So here is what the solution looks like. Oh, let's compute what the gradient of f epsilon x is. What is gradient of f epsilon? So it's c minus epsilon. What's the gradient of summation of log x?
One over X.
1 over x1, perfect. 1 over x1, 1 over xn, perfect. What's the second derivative of this? What's the derivative of c? 0 minus epsilon. What's the derivative of 1 over x1 with respect to x? Minus 1 over x1 square and 0, 0, 0, 0, 0. And then 0 minus 1 over x2 square 0, 0, 0, 0, 0 minus 1 over xn square. So I have a negative sign here and I have negative sign along the diagonal. So what I have is epsilon and I'm going to call it x minus 2, where capital X is diagonal of x. So I have the vector x and I'm going to put vector x along the diagonal of a matrix, and I'm going to create this capital X. And this is epsilon capital X minus 2. X is positive. X is greater than 0. So diagonal of x is a positive definite matrix. Epsilon, which is a positive number, times a diagonal matrix with positive entries, it's a positive definite matrix. So this is a convex function in Z. Okay. Any questions so far? Okay. So I'm going to erase this and I'm going to write what x bar looks like as a function of these two terms. So x bar is given by, I'm going to write a lot of different terms, x minus capital X qx epsilon and E one, 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 one. and I'm going to write Q x epsilon equals to x inverse x minus x bar. This is solved using Lagrange multiplier theorem. Okay, so I'm standing at x. I said that let's take 1 Newton step. I'm not going to take multiple Newton step. I guess I'll have to take multiple Newton step in order to get to the central path. But I'm just trying to get warmed up here. So I'm standing at x. I need to figure out x bar, which is one step of the Newton's method. That's given by this expression. So I solved this problem using Lagrange multiplier theorem. So I realized that this is a convex function in Z with linear constraints in Z. So I can use Lagrange multiplier theorem to solve it. I used Lagrange multiplier theorem. I kind of figured out that this is what the solution looks like. Where if I know x and epsilon, I can compute this particular quantity. And once I compute this quantity, I can figure out that x bar equals to x minus this capital X, which is diagonal of x, times this vector q of x epsilon. Okay, what happens if I am at the central path? What happens when x is equal to x star epsilon? If x is equal to x star epsilon, then x bar equals to, so if I am at the optimal point, what is x bar? So if you're at the optimal point, you take 1 Newton step, where are you going to land up in? Anyone wants to guess? If you're at the optimal point, you are at x star, you take a Newton step, where will you go? You will remain at that point because you're already at the optimal solution. So in fact, if your x was equal to x star epsilon, then x bar will be equal to x. If I'm at the optimal point, I take a Newton step, I will be at the optimal point itself. I'm not going to move. So what is this q of x epsilon? It's some transformation of x minus x bar. So in some sense, the thought process here is, how do I know I'm close to the central path? If this vector turns out to be small. If this vector is small, it means that x is close to x bar, which means that I'm close to the central path. If x bar is far away from x, which means I'm far away from the central path, so I take a Newton step and I have to jump a very long distance. So x bar is far away from x, which means that q has to have a large magnitude. And this is something that I can compute. This is something that depends on the current point x and the current epsilon that I have picked. So in fact, the norm of this particular vector q is going to give us some information about how close or far we are from the central path. Okay, so norm of q a measure of closeness to the central path. Okay, so I start with epsilon equals to 100. I start with some random initial point in the space. I want to go close to the central path. I take multiple Newton step. So I apply this algorithm. I take multiple Newton step and I look at the norm of q. So let's say at the beginning, norm of Q was 1 million. I'm very far away from the central path. I'm going to take one more Newton step. My norm of Q is now 100. I'm closer to the central path, but I'm going to take one more Newton step. My norm of Q now becomes, I don't know, 0.5. It means that I'm very close to the central path now. Now, remember this algorithm in its original form, it's saying that we have to keep reducing the value of epsilon from infinity to 0. I can't go to infinity, so I'll start with some large number, maybe 100, maybe 1,000. And I'm taking multiple Newton step, but I can't keep going on forever because there is an outer loop where I'm changing epsilon, and then there is an inner loop where I'm changing x. And I cannot take infinite number of steps because I want to terminate this whole algorithm in a finite number of steps. So at some point of time, I'll have to stop updating. I'll have to stop taking the Newton step, and then I'll have to update epsilon. So what would be a reasonable value of Q or norm of Q when you should stop? So it turns out that the algorithm is, if norm of Q is less than 1, you stop, you change the value of epsilon by a specific factor. So you multiply epsilon to some number, 0.9 maybe. We'll talk about it in a bit. And then I'm going to take one more Newton step, okay? And then I'll change the value of epsilon again. Then I'll take one more Newton step. Then I'll change the value of epsilon again. So alternatively, I'll keep taking one Newton step at every point of time and change the value of epsilon. I'll do this alternatively, and eventually I'll converge. As long as epsilon goes to a small number, I'll converge to the optimal solution. So here are 3 important facts that leads to this conclusion and the algorithm. Let me write it here. These propositions that I'm going to talk about, they are proved in the book. The proofs are fairly long, so I'm going to skip it in the class, but you can read the reference and figure out what the proofs are. So proposition 1, my x is greater than 0, ax equals to b, norm of q x epsilon less than 1, then C transpose x minus f star. So this is f star. It's the minimum value is less than equal to epsilon times n plus square root of n. Proposition 2, x greater than 0, ax equals to b, qx epsilon less than 1 implies x bar epsilon. Okay, maybe I'll write it in the second line. How do I know that I'm close to the optimal solution? So f star is the optimal value, x is where I'm standing right now. So C transpose x minus f star is less than equal to epsilon times n plus square root of n. So what's the value of n? 1000, okay, something like that, 1000, 1 million, depending on the application. So let's say n equals to 10 raised to 4, okay. So n equals to 10 raised to 4, square root of n is 10 raised to 2. I want to get within, so let's say my accuracy requirement is 10 raised to minus 6, okay. What that means is I want my C transpose x minus f star to be 10 raised to minus 6. What should the value of epsilon be for n equals to 10 raised to 4? So if my accuracy requirement is 10 raised to minus 6, my epsilon should be 10 raised to minus 10, right? That's my requirement. I need to keep reducing the value of epsilon until I reach 10 raised to minus 10, at which point, because of this result, and as long as q of x epsilon is less than 1, it means that I'm close to the central path. I can say that, look, I'm close to the optimal solution, I'm going to terminate. Okay, perfect. So I need to go all the way to this particular epsilon. Now, how do I pick epsilon? So this one is saying that, look, if you start with a point which is close to the central path, you take 1 Newton step, you definitely get closer to the central path, okay, which is not surprising, but at least I get an exact expression of how close, or an upper bound on how close I am to the central path within 1 Newton step. Awesome. Now so let's say I'm close to the central path, and this norm of q is less than equal to gamma, which is strictly less than 1. I'm going to reduce the value of epsilon. So epsilon is getting multiplied by something that is less than 1. Delta takes a value which looks something like this. So roughly this is 1 minus 1 over square root of n, okay. So what is 1 over square root of n? 1 over 100. What is 1 over 100? 0.01. So I'm going to multiply epsilon by 0.99, okay. If delta was equal to 1, of course delta has to be picked in a certain way, but I'm just approximating it to be equal to 1, and I'm going to use delta equals to 1. So I'm reducing epsilon by a factor of 0.99 in order to get epsilon bar, and I'm taking 1 Newton step. It turns out that q of x bar epsilon bar is also going to be less than gamma, or less than equal to, or less than, let me just check. Less than equal to. Okay, so in some sense, what's happening is every time I take a Newton step, I get closer to the central path. Then I pick an epsilon bar by multiplying epsilon by some factor, let's say 0.99 in our case. Then I remain close to the central path, and I'm back to this particular position where I need to take 1 Newton step and then change the value of epsilon bar again. So that's the algorithm that was designed in 1984. It has the best performance in the worst possible linear programming problem that you would ever encounter. Okay, worst possible linear programming problem. The manifold suboptimization method that we talked about, the worst case performance there is exponential, because you could have exponential number of edges that you need to traverse in order to get to the optimal solution. So let's say the optimal solution for in the manifold suboptimization case, let's say it's that particular corner, and we started from that corner. Then I have to traverse all these edges, and I have to reach there, and there could be 2 raised to n edges in a problem with lots of inequality constraints. So manifold suboptimization method is really bad. in that particular respect because you have to take exponential number of steps. So you can always create the worst possible problem, linear programming problem, where you have to take exponential number of steps to get to the optimal solution. But not this one. This one is the first algorithm. Well, not quite the first algorithm, but among the first algorithms to come out that said that for linear programming problem of this type, you can reach the optimal solution in polynomial number of steps in the worst case. And this is polynomial in n. So it's order of n raised to 3.5. That's the complexity. Okay. And then, of course, a lot of stuff happened. After that, you can go and look up Wikipedia on this particular algorithm, and you will get the history of what this algorithm is how the history evolved at that point of time in 1980s. Now, going back to the picture, let's say this is my convex set. This is Ax equals to bx equals to b, x greater than equal to 0. And this is my central path, x star epsilon. And this is my optimal point, x star. And this is my initial condition, x naught. Let me call this x star infinity. And this is x star of 0. What am I going to do? I'm going to take a few Newton steps and I get close to the central path. This was my x star of epsilon 0, this point. So I get close to this point. Now I need to take I need to reduce the value of epsilon, and I reach here, and this is my x star of epsilon 1. And starting from this initial condition, I want to reach closer to this point because now I have changed the value of epsilon to epsilon 1. I'm starting from here. I'm going to take 1 Newton step, and I get closer to x star epsilon 1. Then I reduce the value of epsilon 1 again. Now this is my x star of epsilon 2, and I'm going to take 1 Newton step, and I'll reach here. And then here I change the value of epsilon again, and I'll keep going. I'll keep tracing the central path somewhat approximately in order to get to this particular point. So initially you have to run multiple Newton steps. Later on you need to run only 1 Newton step at every point of time. Can you think of a faster alternative for implementation? Let's say you were supposed to implement this algorithm. Go back to 1984. You're working in AT&T Bell Labs, and you are asked to implement this algorithm. How would you speed up this algorithm further? You don't have to come up with theoretical guarantees. All you have to do is speed up this algorithm. What would you do? What is slowing this algorithm down? Which step among this is slowing the algorithm down? Yes.
I think first we need to get near to the central path, then we are going.
Then you are going to trace the central path. So which is the step that's very restrictive? So remember we said when n is 10 raised to 4, this term is 0.99. So reducing epsilon extremely slowly. And you need to get to epsilon 10 raised to minus 10 as soon as possible. That's what our eventual goal is. So if I start with epsilon equals to 100 and I'm multiplying it by 0.99 every time, I'm going to take a very, very long time to reach f10 raised to minus 10. So how would you speed it up? I want to change the value of epsilon. I want to reduce the value of epsilon multiple, like by some order of magnitude. So I want epsilon k plus 1 to be equal to 0.1 times epsilon k. Okay, so I'm not following this recommendation anymore. Then how do I remediate? So I went from x star epsilon 0. I was supposed to come here, but instead I'm trying to reach here. I've reduced my value of epsilon by a factor of 10. So now this is my x star of epsilon 1. How will I go from here to here? I'll have to take multiple Newton steps, right? So 1 Newton step can only get me here, and then I'll have to take multiple Newton steps to get closer to this particular point. So the original algorithm is called short step method. This has a good worst case performance. So you can prove theorems about it. The implementation is done via long step method. Where epsilon k plus 1 equals to 0.1 epsilon k and multiple Newton steps. Per iteration. Okay, so if you are a PhD student, you should love this method because you can prove theorems. If you are a master's student, you should love this method because you don't have to prove theorems, you just get to converge faster to the optimal solution. So that's the barrier method for linear programming. We are specifically using a log barrier function. Of course, you can come up with your own set of algorithms by picking some other barrier function, such as inverse barrier function that we talked about in the previous class. That's called affine scaling method. If you use minus 1 over xi as your barrier function or 1 over xi as your barrier function, then that method is called affine scaling method. This method is called Karmarkar's algorithm. That's barrier method with logarithmic barrier function. And you can look up the Wikipedia for all the historical tidbits of information on this. Any questions so far? Is the method clear? Okay, so we want to trace the central path. So that's this method is only for linear programming, but you can pretty much do the same thing for nonlinear functions as well, except that none of these guarantees will be there because these guarantees are only for linear programming method. But the idea of this approach, which is you think about a central path in your brain, and then you are doing multiple Newton steps in order to get close to the central path, and then you are trying to trace the central path, is basically how the barrier method would be applied for any arbitrary nonlinear problem with a bunch of constraints that could be nonlinear in nature. Okay. Any question? No questions? Wonderful. So let's talk about augmented Lagrangian method, which is the next method. Remember, we have to do 4 methods in this part. So we've done the first method, which is barrier method. Now we'll talk about augmented Lagrangian method. What is the problem statement? I want to minimize f of x such that h of x equals to 0 and x is in some convex set capital X. We will discuss mostly the case where x is equal to Rn. The set is Rn, but for now, let's try to be a bit general and talk about the case where you have a convex set and you're trying to optimize this function with equality constraint. We define what is known as augmented Lagrangian, which is given by LC of x lambda, which is f of x plus lambda transpose h of x plus c over 2 norm of hx square. Okay. So this one is Lagrangian. This is the usual Lagrangian. And then you add the c over 2 norm of hx square. That makes it an augmented Lagrangian. So augmented Lagrangian is LC, L subscript c, whereas the usual Lagrangian is L of x lambda. So the c denotes the augmented part, which is this. This is the augmented part of the Lagrangian. So suppose I want to solve this problem, and instead of solving this problem, I'm solving this particular problem. Let's think about it. What am I going to get by solving this problem? So I don't have any equality constraint there. If I'm solving this problem, I don't have any equality constraint. So I've gotten rid of the equality constraint, and instead now that's part of the optimization function. I have to pick c and lambda because I don't know upfront what c and lambda is. I'm given this particular problem. Nobody has told me what c should be. Nobody has told me what lambda should be. But what I've done is I only have an optimization problem. So if I pick c and lambda, if God comes and tells me what c and lambda I should be picking, then I only have a problem of optimization over a convex set, which is easy to solve. I mean, easy to solve in the sense that we have learned a whole bunch of algorithms on how to optimize a function over a convex set. So we can apply those algorithms here and solve it. Now, how should I pick c and lambda? What do you think the purpose of c here is? If I'm trying to minimize this augmented Lagrangian function, what role is the c over 2 norm of hx square playing? Should the value of c be small or should the value of c be large? Should I pick c equals to 100, 1000, 1 million? Or should I pick c equals to 0.001? What do you think? What makes sense in this particular case?
Small.
You want c to be small?
Yeah, because if it gets bigger, it's just gonna go.
Right. So if I pick c closer to infinity, then these terms are dominated by this term, right? This term is the most dominant term. So I guess c should be small. But by small, do you mean 100 or do you mean 0.01? Right? Both of them are small c's in comparison to c going to infinity.
It's too small. There's a normal
Right. So if I take c to be too small, then of course I'm optimizing this particular function, but then my h of x could be non-zero. Okay. All right. So the idea is c should not be large, because then I'm not optimizing this, I'm just optimizing this function. And c should not be small, because otherwise I might get a value of h of x such that it is non-zero. So therefore, I'm not solving the original problem that I was given where h of x has to be equal to 0. Okay, so you can do two things. Option 1, pick lambda approximately equal to lambda star and c small. Or the second one is you take C large, but we do have a problem. As we discussed, we have a problem here that if you pick C too large, then we might be solving a different optimization problem, not the original one. Okay, how do I know what value of lambda should I pick? So all I have to do is make sure lambda is close to lambda star. What is lambda star? We've done a bunch of problems where we have figured out that lambda star or mu star are in some sense prices or profit or marginal profit and things like that. So if I know the prices from yesterday, then I can use similar value of lambda for today as well and solve this optimization problem. So in some sense, because you are solving this problem on a day-to-day basis, you could have a good approximation of lambda star, and then you can just use that lambda here in order to solve the problem. Awesome. So let's look at the first case where I have x k equals to argmin LCK x lambda k. X is in capital X. So I pick a sequence of lambda k and ck. And the proposition is X closed lambda k bounded ck less than ck plus 1 for all k. Ck goes to infinity. Then every limit point of xk is global minimum of this problem. Let me call this star. So if x is closed, lambda k is bounded. Generally speaking, you would pick a value of lambda k and you will stay with that lambda k for the rest of the iteration if you wanted to apply this algorithm. So this will automatically be satisfied. Lambda k would automatically be bounded. You are letting ck increase to infinity. So in the previous case, we were letting epsilon k go to 0. Now we are taking ck going to infinity. And then I'm getting a sequence of xk, which is going to be a global minimum of this particular problem statement. But remember, I'm talking about global minimum here because I'm solving this particular problem. So this is arg min, this is not arg local min. Okay. So if you're only computing local min of this particular function, then this would be a local minimum of star, not a global minimum of star. But because we are using global minimum, so what we get is a global minimum of this original problem. So that's the first method. The second method, which is more interesting, Any questions on this? I don't think this is particularly interesting, but definitely good to know. But the second proposition is more interesting, where my x is in Rn. So my x is the entire set. Okay, so let's say xk converges to x star such that gradient hx star is full rank and lambda k is bounded. Then lambda k plus ck hxk converges to lambda star. That satisfies and h of x star equals to 0. Okay, so now we are in a setting where x is equal to Rn. So I have to solve this unconstrained minimization problem of the augmented Lagrangian. Once again, I'm picking a sequence of lambda k and ck. Ck is going to infinity. So ck goes to infinity. Assume that this sequence xk is converging to some point x star such that the x star is a regular point. Remember what the definition of regular point was, that gradient of h is full rank at that point. So gradient of hx star is full rank. So xk is converging to a point which is a regular point. Lambda k is bounded. So the sequence lambda k I took appears to be a bounded sequence. In that case, if you add lambda k plus ck h of xk, it converges to lambda star, which satisfies the first order necessary condition for optimality. So h of x star equals to 0 and the first derivative of Lagrangian is equal to 0. Does that mean that x star is optimal? Remember, necessary condition is a slippery slope. It's just a candidate for an optimal solution. You don't know whether it's optimal or not unless you check for a sufficient condition, but at least it is something. It's not really a bogus point. It is some point where the first order necessary condition is being satisfied, and that point also lies to be in the constraint set. Our constraint is h of x equals to 0. This constraint of course doesn't apply because now we are in Rn setting, and so h of x star is equal to 0. So we are at a point on the manifold where first order necessary condition is being satisfied. So based on this particular result, we'll define a method called method of multipliers in the next class, which in the method of multipliers, we will use this as an approach to update lambda k at every point of time. So we'll talk about method of multipliers and then we'll talk about sequential quadratic programming. So thank you so much and see you on Wednesday.